our next topic for magnetic fields is magnetic flux and Gauss's law for magnetism. Now, we're only going to briefly touch on this today, but we're going to see that when we get on the topic of electromagnetic induction, this is going to come back into play and be huge. But for now, we can define magnetic flux as essentially the density of the magnetic field lines that pass through a surface. So we're going to walk through this much faster than we did with electric fields because we've already seen it. It's basically the same thing. So if you have a magnetic field shown here, and we could count the lines, okay? We can't actually count the lines because we could have an infinite number of lines passing through that surface, but this kind of gives us a feeling of the density of the field lines. Now, we define the surface area to actually have a vector A, and as long as that vector A is parallel to our magnetic field B, then we can define our magnetic flux, and they're using an M. I think a lot of times it's used as a B to be consistent, but either way, you have electric flux and we have magnetic flux. Either of those symbols will be fine. And that magnitude of that flux would equal B times A. You'd have the product of those. If the surface is tilted, we have fewer lines passing through, and that's because our surface area vector A is at an angle now to our magnetic field, that same angle by which the surface was tilted. So we would find the component of A that is, well, that was kind of the wrong spot, that is parallel to B, in which case that would be the cosine of that angle. And that would give us our magnetic flux is BA cosine theta, or BA parallel. And this is not Physics 103 for this class, but same idea. We end up with a dot product. And then if the magnetic field is not uniform and the surface isn't flat, you may have to integrate across the surface by taking a little tiny infinitesimally small piece of the surface area and add up for each of those little surface areas on that surface, accounting for the fact that they could have different angles. In which case, that's the same thing as taking an integral. So we'd have the integral of B dot dA. We could then do this for a closed surface. And our closed surface would have different surfaces. We would have a surface on the front, we would have a surface on the back, and then we would have this surface kind of along the side, so you would have to add up the flux through each surface. And then we use that little circle there to represent that we're integrating over a closed surface. This would actually be a double integral with our goal of never actually having to solve that double integral. And we also defined Gauss's law that said basically your flux with the electric field is based on whatever charges are enclosed. And if you have either no charges enclosed or no net charge enclosed because your same number of positive and negatives are inside, you would have no net flux. Well, in this case, magnetic monopoles, we said, don't exist. So there is never going to be any case in which we could enclose only a north pole or only a south pole, which means we're always going to have equal numbers of field lines going in and out of this closed surface. So what this tells us is that Gauss's law for magnetism basically states that the magnetic flux over a closed surface is always zero. And this equation is one of Maxwell's equations. So we've had Gauss's law for electricity. Now we have Gauss's law for magnetism. And that is going to be another one of those fundamental equations that defines the relationship between magnetic fields and electric fields. So because it always tells us there's no enclosed flux, it doesn't really give us anything to do with it at this time. So we're going to table our concept of magnetic flux, save it for later when we start looking at electromagnetic induction, which relates to changing flux. So what we now have is these two equations. We have our electric flux is E dot dA. It's equal to Q enclosed over E naught. We have our magnetic flux is the integral of B dot A and that always adds up to 0. The unit for magnetic flux is the Weber, which is the WB, capital W, lowercase b. And as we go through, we're now going to switch phases and instead look and move on to the magnetic forces that act on current carrying wires. So we're tabling our discussion on flux. You'll see it again later. But now we're going to look and see what's going on with magnetic forces on current carrying wires. So we've talked about the fact that our magnetic forces act on moving charges. Well, a current carrying wire is basically just moving charges. So if we just kind of relate those together, we see that the magnetic force on a current carrying wire is equal to IL cross B, where L is going to be the length of the wire, I is the current through the wire, and B is the magnetic field. So these look really, really similar. And this is actually the one that we discovered first because we had discovered current before we had discovered electrons. So this was come up from experimentation, but it is possible to derive this relationship through other means, which are beyond the scope of this course. However, we can directly relate these two equations and see why it makes sense. So why does this make sense that those relationships are the same? So picture that you have a current carrying wire and you have the north side of a magnet and the south side of a magnet so that there is a magnetic field going that direction. So what we do in this case is we want to compare kind of our understanding of our force is equal to QV cross B to our equation that force for a current carrying wire is IL cross B. Now, the first thing I want to recognize here is that L is a vector, current is not. So what we're defining is the vector L is the length of the wire, and L has the magnitude of the length of the wire and the direction of the current. So L is always in the direction of current. So if you think it's weird for the length to be the vector, you can just pretend like it's the current that's the vector, okay? And this is going to be our conventional current. So what we want to picture is this wire. Let me kind of erase what we got here. You can picture that you've got this wire, and if you were to take one infinitesimally small section of this wire, that section of the wire is going to have some sort of small charge moving through it, and that in a certain amount of time, it's going to move some distance dx, okay? And it's going to be moving at some speed. So in some amount of time, dt, it's going to move a distance of dx. Now we're going to assume that our current is constant. So what I can picture is I have my force is equal to QV cross B. But for the wire, that little charge is only giving one infinitesimally small little tiny force. So I could picture that that is dF is equal to dq V cross B. So that would give me the little tiny bit of force that the magnetic field would be applying on the wire due to just that little tiny dq. And if I define my velocity as being constant, I can define my velocity as dx dt, the rate of change at that position over time. So I can plug that in and I get df is equal to dq dx dt, and dx is a vector in the direction of the length, cross b. Now, because what I have here is multiplication division that can occur in any order, I can reorder that, and I get that df is equal to dq dt times dx cross b. Well, dq dt, I think I've seen that somewhere before. That is our definition of current. So I get that df is equal to I dx cross b. But that's only due to this one little tiny section. So I want to figure out what it is for the entire wire. So I'm going to integrate from 0 to L. So if I want to find my whole force, I'm going to integrate from 0 to L. I is a constant, B is a constant. So that just ends up being the integral of dx, which is just x. So that gives me that my force is equal to IL cross B. And that L is a vector because x is a vector. So that is where that equation comes from. Now it's a cross product, which tells us that the force is going to be largest when our wire and our magnetic field are perpendicular to each other. And we're still going to be able to use our right-hand rule. And we use the right-hand rule for the conventional current, because we assume that our conventional current is the movement of positive charges, and our right-hand rule always works for positive charges. Well, what happens when your wire is not in a straight line and perpendicular and so forth? So what you could do is you could use that cross product, and you could find that your force is going to be I LB, and you could do sine theta as long as you have L and B, and theta is the angle between those vectors. Like I said, we assume that our conventional current and L are going to be in the same direction, and I can use a right-hand rule, and I can see for this straight wire, for the portion that is in the field, that there is going to be a force acting to the left, because I would point my fingers in the direction of I, my palm is into the page, so my thumb is going to be pointing towards the top left where that force is. Now, one thing to be careful of is if my magnetic field is only this section, the length of the wire that I use is only the portion that is in this section right here. I do not include the portions of the wire that are outside. Okay, so this works for individual charges, it works for a whole current carrying wire, but it works in this form when you are working at constant magnitudes, constant directions, and so forth. But what if the wire is not actually straight? So what you'd have to do is you would have to work through and break this wire up into pieces, because every little part that you look at is going to have a slightly different portion. So you would take a small tiny portion of the wire. They're using a DS here. I usually use DL. I think at some point along the line, the person that originally started these PowerPoints switched to S, because to make this little curly L, lowercase l, is very difficult to do in PowerPoint, so they just switched to S. They also use S in calculus for position, so it's something that you might see. So if I take this little infinitesimally small section of the wire and do IDL cross B, I would get a force. In this case, I would have to have my palm facing up out of the page, fingers kind of down into the right. That puts my thumb kind of down into the left for the little tiny force for that section. But if I was to pick a different section, say I was to pick this little section of the wire right here, then I'm going to have that DL or that DS right there, and then my force is going to go that way. Or if I was to pick a different part over here, you know, every little different part is going to give you a slightly different direction for that. So I'm going to have my DL, and then I can use that cross product, and I could find that that force is going to be like that. And then basically what you'd have to do is you'd have to add up all of the X and Y components, figure out what cancels, and you would end up integrating in order to find your value. So a more correct version of this is that the force is equal to the integral of I dl cross B. Now you can pull that I out in front as long as that current is constant. Okay. Otherwise it would technically need to stay within the whole integration right there. Now you're not going to see weird wibbly wobbly shapes, but you might see something like this where you have straight portions and you have like a semicircle or you have a full loop. So we want to actually find the net magnetic force acting on this wire. So the first thing we need to do is break it up into pieces. So we have 3 sections, and And the sections that we look at are only the sections that are inside. So if the portions that are outside, we can completely ignore. And then within those sections, we have two straight sections and a curved section. So if we look at first at the two straight sections, because they're straight, we can just use the IL cross B version of this equation. So if you put L as a vector, as pointing to the right, and you use your fingers with the right hand, I point them towards the right, my palm is into the page, that's going to cause my thumb to point up. So each of those two sections are going to experience a force pointed towards the top of the page. So because the current element and the magnetic field are perpendicular to each other, our angle is 90 degrees, so our cross product is just ILB. So both of those forces just end up equaling ILB. Now the semicircular section is much more difficult. So with that semicircular portion, we have to consider that every little piece is pointing in a different direction. So what you would do is you'd set up and pick one small section. Okay, so DS or DL, whichever one you want to go with. And you picture essentially that little tiny section is part of the arc. So I have actually an arc length here. And I assume that my DS is equal to R d phi. They're using phi here instead of theta. I'm not sure why. That's what they decided to do. So there's going to be some small change in angle that occurs for that section. And that little section is creating a force. dF is going to equal I, because our I is constant. And then it is going to be DL or DS, I'll just keep with DS right here, cross B. For that one little tiny section. You can use your right hand rule for that section and see that your thumb is going to be pointing up and to the left where that DF is. If I was to choose a different section, say I was to choose the little section over here with that little DS, then what would happen is that would cause my force for that one to be up and to the right instead. So what's going to end up happening is you're going to have to add up each of those, and they're going to have X and Y components that you have to deal with. So with this, we can take this definition of DS and we can sub in here, and recognizing that these are going to be 90-degree angles for everything, so I don't need that cross product because my DS is already perpendicular to B. So I can write this as DF is equal to just I ds B, and then sub in, so we get DF is equal to I R d phi times B. Now in this case, R is a constant because that's a fixed radius loop. I is a constant. B is a constant. So if I wanted to define this, the only thing that's varying is that d phi. So I'm going to pull that out at the end. So dF is equal to IRB d phi. Now the problem is that we have both X and Y components to deal with. All right, so we can see that my force is going to have X and Y components for that little bit that we chose right there. So if you were to break this into components, I know they show dFy right here, but I'm actually going to use this triangle over here where that's dFx, and then I have dFy right there. And the reason I do that is actually because phi is right here, and because we're going to integrate in terms of phi, and phi is my angle right there that I'm starting at for this particular point, I'm going to use that. So what happens is I have that dF is equal to IRB d phi. And then I can define the X and Y components for that. And so I could define dFy as equaling IRB d phi, And then my y component is the opposite side of that triangle, so it's going to be sine of phi. I can also define my dfx to be IRB d phi cosine of my angle phi. So if I was to go through and work this up, I, R, and B are constants. So if I wanted to integrate dfy, I'm going to integrate dfy from 0 to fy, because I'm going to assume when I start over here that I haven't acquired any of the charge, any of the current, so I don't have any force. And by the time I get to the other side of the wire, I'm going to be at my full force. And then I'm going to have IRB as constant, so I'm going to integrate, and I'm going to start here when my angle is 0, and I'm going to go over here to where my angle is pi. So I'm going to do that semicircle. So I'm going to go from 0 to pi of sine phi d phi. So the integral over on the left side is just going to be fy, and then I'm going to get IRB. The integral of sine is negative cosine, evaluated from 0 to pi. So you always want to show your integration and then show your substitution of the limits. So fy is going to be negative IRB of cosine of pi minus cosine of 0. So fy is going to be negative IRB. Cosine of pi is negative 1 minus the cosine of 0 is a positive 1. So negative 1 minus a positive 1 is a negative 2. The negative cancels with the negative up front. So I get that fy is going to be 2 IRB. So that is the y component. If I look at another section over here, like we did before, if I was to look at this section again, and I know that that df would be over up on the opposite side. If I was to break that one into components, I would get dfx, and I would get dfy. So I can see that if I look at those two sides that have symmetry, that the y components are going to both add up. They're both pointing up. That's going to be true for all parts of the circle, that the y components are going to be in the positive y direction. The x components, though, are going to be on opposite directions, and there's going to be symmetry. So those x components should actually all cancel out. So I could say that when I integrate from 0 to fx, and I integrate over here from 0 to pi, I know that fx is going to have to add up to 0 because of symmetry. If you needed to prove it, you could then do the same thing. The integral of cosine is sine, and then you could show the substitution of sine of 0 and sine of pi, and you would find that you're going to end up with a 0 value for those, because those are actually going to cancel. If you wanted to see that derivation for the x component, it's here on the slides. So therefore, to see the total force, the forces of the three sections are going to add up. So you're going to get ILB plus ILB for the two straight sections, and then 2 IRB, and that is going to give us our force for that whole section. So you could see something like this with like straight line sections or semicircular sections. You're not going to see crazy like wibbly wobbly wires or anything along those lines. So here's another example. We have a semicircular closed loop of radius r carrying a current of I. It's fully enclosed in the region, and we want to know what is the net magnetic force on the loop of wire. Well, we're going to draw on what we've already done. So we know that that semicircular section from the previous result is going to be IRB. Sorry, 2 IRB. And it's going to point upwards. And you could use the right-hand rule to show that. That straight line section with the current going to the left and my palm into the page is going to point downwards using the right-hand rule. So that downward section is going to be ILB, but L is going to be the same thing as 2 times R, because that's going to be the diameter. So that tells us that straight line section is also 2 IRB. And those two sections are actually in opposite directions. So our net force on that wire is going to be 0. And actually, this is true for any closed current loop that is entirely enclosed in a magnetic field. Universally true. Isn't that kind of fun? There's some reasons why that wouldn't be, for example, if it was moving and so forth, but we're looking at the moving right now. So this is just a loop in a field with a current. If it's a closed loop of any shape, square, wibbly wobbly, doesn't matter. As long as it's a closed loop, it is going to have no net force. But just because it can have no net force doesn't mean there's no net torque. We saw that with dipoles in electric fields. So what happens is that we can take a loop of wire in a magnetic field, and I'm going to assume that this wire is fully enclosed in the magnetic field, even though it's not necessarily being shown exactly in the diagram. And what we can do is we can figure out what's going on with the torque. So we're going to assume that there is a counterclockwise current going through this wire, and that there's one side has a length of L and the other side has a width of W. If we break this into pieces, we can see that there is no force on the horizontal segments. Those are these segments right here. And that's because the current at those sections is going to be parallel or anti-parallel to the magnetic field, so the cross product is going to be 0. So those two sections are not going to be affected by a force. The vertical segments are going to experience a force. So if I look at the first section on the left, the current's going down. So if I point my fingers down towards the bottom of the page, I rotate my palm to face the magnetic field on the right, that forces my thumb to point upwards. So I'm going to have a force upwards on that left side. If I look on the right side, that current is now actually coming up the opposite direction. And then if I do IL cross B, that's actually going to give me a force that is into the page. Now those forces are going to be equal and opposite. And they will have magnitudes equal to ILB because everything's perpendicular. But there is going to be a net torque, and this is going to cause a rotation. So if I just kind of look here briefly, and I use that my torque is equal to R cross F right-hand rule, there is going to be an axis about this which can rotate about. And so I could define that axis and have that force as being a distance R to the left. And if I point my fingers in the direction of R to the left, and I point my palm up out of the page where the force is, that's going to show me that my torque, my thumb, actually points up towards the top of the page. And if I were to curl my fingers, that's going to force my fingers to come up out of the page and want to curl up and over that wire. So that left wire is trying to come up out of the page. At the same time, if you do the other side of the wire, with R pointing to the right, if I point my fingers in the direction of R, my palm into the page, my torque is still going to be up towards the top. So my torques are going to add, and I can see that if I were to curl my fingers with my thumb up top, this right side of the wire is trying to go down into the page. So these torques are adding up to cause a rotation. So that rotation would be based on the half of the width of the wire. That's your R values. So if you use the torque as R cross F, at this particular orientation, R and F are going to be perpendicular to each other. So that torque is just going to be W over 2 times FR. Our FR is ILB. So the torque on each section is going to be 1/2 WILB. Now, we defined the area of the loop to be based on length and width, so the L times W is just the area. And when you add those two together, the total net torque is going to be IAB. So A is the area, I is the current, and B is the magnetic field strength. Now, what happens is this is going to start rotating, and the force is still going to be straight down, but now you're going to have an angle between the R value and the force. So you need to find the components of those that are perpendicular to each other, which are going to be based on sine theta. So then when you take the sine of the angle theta and add that in there, you end up with IAB sine theta. So this is more general because it applies to all the different orientations, not just when they're perpendicular to each other. And then if we define the area to be a vector, so that's what this is showing right here. If we define the area to be a vector, we've seen surface area vectors before, then that surface area vector is going to be a cross product with the magnetic field. Okay, because we're looking for when those are perpendicular to each other, that is when it's going to give us our torque. So we can generally define this IAB with IA cross B to account for when B and A are at different angles. So here's my B, here's my A, and theta is the angle between those. Now, we saw this with dipoles. We could also define what we call to be a magnetic moment. We've talked about little magnetic dipole arrows. We saw those in the very first lesson on magnetic fields. And we use the Greek letter mu with an arrow on top to represent the dipole moment. And we define that to be I times A. So that's going to define kind of how this loop kind of relates in its orientation to the magnetic field. And then we can therefore define more generally that our torque is going to be the dipole moment cross B. And that dipole moment is going to be a vector that is in the same direction as A. If our dipole has, if our loop has more than one loop in it, so a lot of times we have wires that are coiled, then we can multiply this magnetic moment by however many loops there are. So we could also more generally define mu as equal to NIA, where N is the number of loops. So if we have this torque, then we are going to have this relationship with energy as well. So our current loop creates a magnetic dipole by having that loop area come through it. We've seen the electric dipoles, and we had that our torque was P cross E, where P was our dipole moment, and our potential energy was negative P dot E. Our magnetic dipole is going to be mu cross B, and our magnetic potential energy is going to be negative mu dot B. So these are very similar. We're not going to go through the whole derivation for this one. It doesn't come up very often. The torque is going to come up much more often in problem solving because that rotation that we're seeing of that loop of wire is kind of how motors work. So motors essentially work on this principle. So if you were to have a loop and you were to put it in a magnetic field, if you could get that loop to start rotating, that magnetic field with that current running through it is going to get turned in that magnetic field, creating rotation. Now, the problem with this is that the way the torque is going to work, kind of with the dipole, is the tendency is not to rotate 360 degrees because the torque is going to change directions halfway through. So instead, what happens is the tendency is to oscillate back and forth. But if I want a motor that is going to turn a wheel, I want it to be able to go 360 degrees. I don't want a car that just goes back and forth, back and forth, back and forth. So how am I going to get that 360 degree motion? Well, what's going to happen is I'm going to need to find some way to either get the current to flip directions or to get the magnetic field to flip directions. And so the easiest way they do that is to actually get the current to flip directions. And they usually have a device which is called a commutator in a motor that flips the direction of the current every time a half oscillation goes through, so that you will get that oscillation to keep on going. So here's a little more detail kind of on how this works. So if you have, say, a current that's coming through here and going this way, in the orientation, you're going to have a force on the upper wire, the left wire, going up. The force on the right wire is going to go down. That torque is going to cause the rotation. Now, when it gets halfway, when it gets straight up and down, if the wire was actually straight up and down in that field, then you would have that the currents are going to be parallel to the magnetic field. And what's going to happen is you're not going to have a torque anymore. But it'll still have momentum because it's been accelerated by the torque. So it'll keep going over the top. But at that point, we need the motor to keep rotating. So what they have is they have like a commutator or some sort of alternating coil that is going to cause the current to move the opposite directions. The commutator physically has a gap here in between the two metal electrodes, and as the wire rotates, different parts of that are going to come in contact with the wire, and that's going to cause the circuit to flip directions. You can also just apply an alternating current, and that alternating current's going to go from positive to negative to positive to negative as it goes through, and that's going to cause the torque to switch directions. Kind of difficult to do here in a static drawing to walk you through this, so I'm going to link some videos about how the motors work, and because they make really good conceptual questions, and plus, you guys mostly drive cars, you've ridden in cars, you use a lawnmower or anything else that has a motor in it. This is really, really good physics. So make sure you actually watch those videos and learn a little bit more detail about how motors work.